So, yes, welcome back to our weekly discussion sessions for the Physics of Nanoscale Devices NPTEL course. My name is Jyotishwaran. I am a PhD student from the ECE department of IIT Roorkee. This is discussions week 7, where we shall focus on the contents from week 7 and 8 of the course. Yeah, the session is now on. So, yeah, as always, I'd like to ask, do the live attendees have any doubts or queries from the previous week's syllabus, from the assignments or anything from the lectures? Any questions?
No, sir.
No questions. Okay, good. That's fine. So, have either of you seen the lectures for week 8?
No, sir. Not started.
Not yet started. Okay, fine. So, this week, what we shall do is essentially go through some of the basic ideas of a metal oxide semiconductor device. So, the primary focus here will be to set up the basic approach for analysis. Like, we shall identify how we are going to study. Yes, Aman?
No, sir. Everything okay, sir.
Oh, okay. No, you saw you were about to say I could hear some sound, so I thought you were trying to say something. So yeah, so the idea is to identify what is happening with a MOSFET device, and from what we have learned so far, essentially the notion of Landauer transport theory and ballistic transport, how can we integrate that? Because most of the students attending this course would have had some kind of introduction to the traditional classical MOSFET devices. So, be it as a part of their electronics devices courses or other VLSI system courses or whatever. But here we will try to approach the same ideas from the perspective of the nanoscale devices. So essentially, we shall set up the basic tools of analysis, and then we shall go on to study the various effects one would encounter in a nanoscale MOSFET, and we'll see which of those effects will aid the functioning of the device and which will prevent the efficient working of it, and how to deal with those effects. So that will be the thrust of the following weeks, like weeks 9 through 11. And the last week, we will cover some additional topics like thermoelectric effect and so on and so forth. So this is what you shall learn in this week, and the following 3 weeks will be like the bulk of the course. So this 4 week content is essentially what the previous 7 weeks of preparation was for. So before we start, I'd give you a preview of the assignment that you guys will be facing. So once again, since we are beginning a new topic, you can see that most of these questions are basically theory based. So, like if you look at question 1, it is essentially asking the dependence of the channel resistance and the gate voltage. So, and again, this is for essentially any kind of a MOSFET. We are not saying that this is a nanoscale MOSFET. So, if there is an NMOS channel, what will happen? And so you can, use the knowledge that you already have, and what we have been discussing so far to solve these questions. So, today's discussion will also be focusing on the theory aspects primarily, but I shall also do like 1 or 2 simple numericals to get the point across. With that, yeah, let us begin the discussions for today's session, because I mean, you guys didn't have any doubts. So, give me just 1 second. Oh, I was not sharing my screen, and you therefore would not have seen the assignment questions. Um, all right, so I will do that again, but just give me a minute. Yeah, can you guys see the screen now?
Yes, sir.
Yeah. So this is the week 8 assignment, which is due in another 3 days, I guess. Yeah. So most of the questions are concept based questions. So if you understand the basics, you should be able to answer all of these questions. So yeah, so based on this, we shall look at the essential features, the properties that we are going to study. So, all right, let us begin our session. So, yeah, so you can see the whiteboard, right?
Yes, sir.
Yeah, okay, so we shall start with a this. So now we are looking at MOS metal on metal oxide semiconductor devices. So we shall still adhere to our original model. So where we have a source, a channel, and a drain. So here where the source and drain are bulk materials and the channel is a discrete or like it's a nanoscopic channel, therefore it will have discrete energy levels, and there will be conduction modes. These things have been discussed before. The fine details of what we have discussed before will not be totally relevant here. However, some of the points that was raised previously will now, like we will now study what will happen, how the microscopic characteristics of the channel will be influenced by the source and drain voltages. So typically when we look at a MOSFET device, the diagram that we might see is we'll have a bulk device. So let us say that is P-type silicon. So in that, usually the source and drain are obtained by doping in the opposite variety. So essentially, this will be heavily doped with donor atoms. So we will have an N-type region here and an N-type region here. And so over here we shall have a layer of insulator, typically SiO2. And on top of that, we shall have a metallic electrode. So this becomes our gate, and of course there are contacts for manipulation of the source and drain voltages. So I have my source and the drain. So yeah, let me just no, I do not want to do that. Yes. So now this, of course, symbolically is represented as a three-terminal device. Yeah, so can someone help me out here? Which direction will the arrow face for a device like this? Either Kamal or Sunita, if you guys are listening.
Okay, sir, you are drawing for depletion type or enhancement? Like,
Good. Very good. So let us, yeah, that is essentially what I wanted you guys to point out. So MOS devices can be used in multiple modes. So we can use it in an enhancement mode or a depletion mode. So right now let us consider a depletion mode device.
okay.
So in that case, what will be my channel characteristics, and therefore like an arrow mark should appear somewhere over here. So if this is my source and this is my drain, which way will that arrow point, and what will be the nature of the channel?
Basically, sir, for P type, the arrow is outward position, and for N type, it's inside. Arrow
Uh-huh.
means arrow goes inside.
Yes. Okay. So is this correct?
For P type.
Uh-huh. So what will be the nature of the channel here? Like when I'm operating my device in depletion mode, how will my channel behave? Like what kind of changes am I trying to induce into this material? Like my aim is to send a current from here to here, correct?
Yes, sir.
So okay, so like let us slowly let us not directly try to answer that question. Let us move step by step. Let me also try to make this slightly more straighter, just for the sake of neatness. Yeah. Yes. So this is my source drain, and this is my channel. So first and foremost, what will the band diagram of this system like? Okay, so before even going to the band diagram, our analysis will essentially contain of two parts. So far, what we have been studying is essentially the transport from source to the drain via a channel. So that is what we have been studying when we have been doing our essentially what is the Landauer theory of conduction. So this accounts for source to, let me just spell that out explicitly. So source to drain transport. For for nanoscale channels. So this is what we have been doing for the past several weeks. So we have been considering short channel lengths. We have taken cases of low biases and uh, like for several special cases we have even explicitly calculated the channel conductivity and evaluated the various parameters. But now we are moving and this was for a two terminal device. So now what we have to do is we have to migrate from the two terminal device picture to the three terminal device picture, because ultimately our aim in this course was to understand the theory behind transistors that have a nanoscale or a mesoscopic channel. I hope you guys remember that from the beginning of the course. So far we have
Yes,
spent
sir.
over half of the course in understanding and analyzing the picture for the two terminal device. Now essentially what we have to do is we have to move from the two terminal picture to the three terminal picture. So when we are looking at the three terminal picture, what we have to consider are the following effects. So ultimately, in all of this, the quantity that we want to study is IDS, the drain source current. Now, just off the top of your head, what will IDS depend on? What should it
Okay,
depend on?
sir. Yes, sir.
Huh?
Basically, sir, IDS is the drain to source current,
Yes.
and mostly it depends on the drain to source voltage, but of
Uh-huh.
course on the gate source voltage also.
Okay.
So, firstly, with the help of VDS, we can generate the electric field, but
Uh-huh.
with the help of VDS, we can generate the electric field in few minutes or few seconds, so that the
Uh-huh.
current increased largely like that.
Hmm. Okay. So this is what you are essentially saying, that it's a function of these two voltages, correct?
Yes, sir. Yes, sir.
Okay, BDS, VGS. And yeah, there is a certain merit to what you're saying. I mean,
And,
obviously, because
uh,
those are the
and sir,
only
also
control.
the
Yes.
yes, sir, and also the effect of dielectric between the metal and the channel. Dielectric also play an important role.
Ah, of course, of course.
Yes, sir.
Like all of that, yeah, that is also a good point. We shall look at that in the subsequent weeks. Like, I don't want to dive into it right now. So, roughly, like, irrespective of what, yeah, so since you mentioned dielectric, let me also uh, like mention that here. So, when I draw this shaded thing, I'm essentially saying that this is a silicon dioxide, oxide, and this is a metallic one type. So I'm just going to say this is metal. Of course, like through our discussions, we'll see that there are now newly or rather relatively recent developments where we can replace this essential structural constraint to have different kinds of gates. So that will also be an integral part of our discussion in the upcoming weeks. So, yeah. So this is the gate is metal because of our, what to say, like that is the M of the MOS, and the middle region is the oxide, and of course the rest is the semiconductor. Um, yeah. So what was I say about to show? Yes, the assignment again. Yeah. So yeah, I know what's happening here. So as you can see, yes, most of the questions over here you are just looking at what is IDS, what is VDS, and what is VGS. So yeah, Kamal, your point is essentially correct because those are the only three voltages. I mean, two voltages we have in this system. It's a three-terminal device. So between them, I can only define two distinct voltages because if I can fix two voltages, the third voltage is automatically determined.
Yes, sir.
Yeah. So this is what we want. So from our aim is to move from our original two terminal picture where we were using, what was the voltage that we were using over here? Like we were talking about a voltage V during our like two terminal device picture, right? So in the three terminal picture, what is that voltage? Is my question clear?
Okay.
Or do you want me to repeat it?
Means, sir, like logo
No, not
voltage.
no. What I'm asking is like, so in this case, like if you remember our previous discussions, I said there is a voltage applied across the source and drain, correct?
Yes, sir.
And for different conditions, we derive different expressions for the current,
Hmm.
right?
Yes.
So now in this three terminal picture, there are two voltages. Which one of these voltages did we previously study? Was it VDS or was it
VDS, sir.
VGS?
VDS. VDS.
VDS. Yes, because I mean
Yes.
the source and drain are labeled here, so any voltage applied across them is VDS. Okay,
Yes,
so
sir.
that was
Because, sir, in the previous, we
hmm,
directly excluded the
existence of the
gate
gate.
terminal.
Yes,
Yes.
correct. Very good. So, so essentially, what we will have are two aspects. So the first aspect is the transport, about which we already have some idea. Now we know how electrons move from the source to the drain through the channel. We have some understanding of that mechanism. Okay, since you guys didn't have any doubts about the previous week stuff, let me ask you a question. Uh, for a ballistic channel, is there any energy loss in the channel itself for the electron?
Not in the channel, sir. Mostly in the interfaces.
Mostly or only?
Only.
Ah, yeah. So
Yes.
if there is a potential drop of V, essentially what happens is on an average, this is not exactly what is happening, but on an average, there is a potential drop of V by 2 jumping from the source to the channel, and there is a further drop, energy loss, when we move from the channel to the drain. So all the resistance effects that we are calculating essentially comes from the channel, source drain interface. Why am I scribbling too hard? I was supposed to.
Yes, sir.
Okay, so that is the point. Now you will see that that aspect also holds here. So essentially, what we have been learning so far is the transport. So that is the what to say, like transport of carriers. So for that transport, like what was one of the quantities that we studied? Like we used we of course we defined the conductance and everything. So in that there was an actual physical quantity of the electron that we used. Do you guys remember that? Like when we wrote all of this, we wrote the Fermi functions, and then before calculating the modes in the channel, we used a very direct physical quantity of the electron for a ballistic channel. We essentially spoke about the average velocity of the electron. Do you remember this? Like when we were calculating the energy broadening.
Somewhat related with mass, sir. Mass
No, no,
of
no, no, no,
electron.
no. This
Okay,
is
okay.
the velocity of the electron.
Yeah.
Like if you remember in this case, like let me just write here roughly. So we had to evaluate gamma of E, which is the broadening, and gamma of V we knew was h by tau of E, which is the transition time,
Yes, sir.
and transit time, not transition time. And what was the transit time? It was
How the electrons are moving from source to the channel region.
yes. So that is this quantity, correct? L by V, Vx.
Mm,
This was done in the previous weeks.
right, sir.
Okay, so actually, when we were doing our two-terminal device picture, we were actually discussing about what the average velocity of the electrons was. So go back and see those things. It's somewhat important, and it will become
Yes.
important once again when we shall talk about injection velocities and velocity saturation in MOSFETs. So this is the quantity that we shall study when we are looking at transport. The second aspect of these devices is the electrostatics. So what do I mean by electrostatics?
Okay, sir. Actually,
Uh-huh.
it means like you are discussing about like some word like capacitance effect
Yes,
between
yes. I mean, true, but it
between
is even more elementary. Even of course, there will be capacitances. I'm not denying that. You will start seeing
yes,
capacitances, but even before we go to the capacitances, electrostatics has a more simpler, direct connotation. What is the first quantity we encounter in electrostatics when we studied electrostatics way back in our high school? So
mm,
charge.
yes, sir. Charge, right?
So that's it. So we are just looking at the stored charge in the channel.
Yes, sir.
If you remember, this was also done in our Landauer picture. We also derived the amount of stored charge in a channel. That integral was also present. Of course, most of the time we were worried with the current integral, but the charge integral was also present.
Okay, sir.
Okay, so now this IDS will therefore, so now, yeah, another thing that we shall consider here is for our discussions. Uh, Typically, we'll be considering 2D channels. Unless and until we explicitly mention that the channel is 1D, the channel, whenever I say channel, I'm referring to a 2D channel. Okay.
Yes, sir.
So that is like, to be considered as a standard from now on. Therefore, the channel will have a length and a width. So ITS can generally be written as the width into like the total stored charge in the channel times the average velocity of that charge. Is this somewhat clear?
Means, sir, the charges are moving with velocity we indicating now.
Yes. So this is a product. I'm multiplying these three quantities. And like I'm
So one
not,
thing,
huh,
one doubt like it's indicating like stored charge in the channel. Then how we can
yes.
correlate this stored charge with velocity?
We are not correlating them. I'm literally just multiplying them. This is not a
Okay, sir.
accurate picture. I'm just saying there is this
Yes, sir.
much charge in my channel, and if that charge gets some velocity, that will be my current. Is that clear? Like, can
Yes,
you?
sir.
This is not. I'm not giving you a current voltage relationship here. I'm not giving you a what to say like device characteristic over here, a voltage current relationship here. What I'm doing is I'm trying to highlight the properties as we are going to study them, and the stored charge is actually determined by both VDS and VGS. Now the
Okay,
velocity,
sir.
of
Okay.
course, depends on certain quantities, but right now I'm going to leave the velocity as it is. You will understand later why I'm leaving it as it is. Maybe not this week, but next week you'll understand that why the velocity is being left alone. Of course, the velocity will also depend on these voltages, but I'm not writing that here yet. It will soon appear. Okay, so now this part is the electrostatics. And of course, now the stored charge, how do we represent the stored charge? You represent it using capacitances. So you are perfectly right when you said capacitances are going to come, but one has to understand what is the effect of capacitances. Like if the capacitance is
Mhm.
high, what is going to happen to the channel? If the capacitances are low, what is going to happen to the channel? Even like not particularly in the terms of like performance characteristics like switching frequencies or things like that. But even before that, if I'm looking at just the current voltage relationship, what will a high channel capacitance give me? What will a low channel capacitance give me? What will the effect of the
Yeah.
body of the device have? Like what kind of what to say, like will it induce an additional capacitance? So these are the things we will have to understand. So that is the electrostatics part, and this is the transport part. So,
And sir, the
uh-huh.
one question is like that we will right now we'll include the effect of gate in this MOSFET. So
Yes.
here the we'll also study the transport property of this three terminal device.
Yes, of
So
course.
sir, my question is like that how this transport gets affected with the VGS voltage, can we also discuss
Of
that?
course. In fact,
Yes.
that will be the last thing we shall discuss today itself.
Okay.
So
Yes, sir.
not only just VGS, but the combination of VGS and VDS. So,
Okay. So
huh,
yes, sir. So sir, question is my like that. Will you draw any graph of that transport? Means how that transition from valence band to conduction band, the
of
effect
course.
with the
I mean
yes, sir.
that is the very next thing I'm going to do. All right.
Yes, sir.
So this is the
Yeah.
idea here. So here I'm essentially talking about the charge and the velocity. So our focus will be on these two things. First, we shall start with the electrostatics. Then the transport will we shall start discussing the transport.
Okay, sir.
And all right. So let me move on to the next board. So now, yes, as Kamal rightly mentioned, we have the band structure. Why are we using the band structure? Because it is a very efficient tool for visualizing the energy constraints and requirements in the device. So first, what is the sequence of materials here? Now, okay, so while studying the band structure, how many directions does this device have? Tell me that. Like for a 2D MOSFET or whatever, like essentially when I'm drawing, yes, let me redraw the device picture again, or can I copy it? You know what, like that might take too much time. Drawing might be simpler for me. Yeah, so when I'm drawing this picture, what I'm asking is, now this is a 2D device and I'm having a oxide layer here, and on top of that I'm having a metal electrode. So this is D, this is S, and this is G. Now what I'm asking is how many, like not how many. Oh yeah, yes. In how many directions does the material profile vary? Like see, if I'm moving from left to right of this device, I start from, okay, yeah, this is P, and like typically this is, since this whole device is P, this regions will be extremely n doped to bring it back to n level. So that will be n plus and n plus, but I'm just writing it as an indicator. Okay. So as I'm moving from left to right, of course, I'm moving from an n-type region to a p-type region to an n-type region. Is there any other direction in which I can move to encounter a variation of materials? Is my question clear?
So mostly we'll try that all the electron move from left to the right.
No, of course, I'm not talking about the electron movement. I'm talking about our picture. Like I have this direction where my environment changes from n-type to p-type to n-type. what if I move in this direction? Will the material properties change as I'm moving in this direction? Of course, it will change because over here I'm at a metallic contact, I'm at an insulator here, and here I'm at a semiconductor. So there can be two kinds of band diagrams. Okay. So now I'm
Okay.
establishing the direction convention. So whenever now I'm going to write an X direction band diagram, I'm going to talk about the source channel drain relationship. And by default, the positive y axis is going to go in this direction. It's going to go downwards. So the y axis starts from the gate, goes through the oxide layer into the body. Okay.
Yes, sir.
So now let us look at the X band diagram. How will that look? Like, let us separately draw the conduction band and valence bands, and let us put them together afterwards. So I have my conduction band and the valence band. Now, where will the Fermi level lie? This is for the source. Where will EF be? Come on, this is easy. You guys should answer this immediately. Can you guys hear me? Hello. Kamal,
Hello.
Sunita, anyone? Yeah.
Yes, sir. Yes,
So,
sir.
where will the Fermi level be for this part?
So for N type channel, na?
No, I'm asking for the source.
Below the conduction band, sir.
Below the conduction band.
So strain.
Like, no, like, will it be closer to the conduction band or closer? Like, it is always going to be below the conduction band, but will it be closer to the
Closer,
conduction
closer,
band or
closer.
okay, yeah, that's what I want.
Yes, sir.
Like, yeah, it's always going to be below. So I'm going to have my EF over here. So this is my conduction band CB, and this is my valence band VB. And now I can move to the, let me use a black pen. Now I can talk about the channel. Now you can ask if it's a nanoscale channel, why am I drawing the band diagram? It will become clear in a bit. So again, I have my valence band and my conduction band. Now where will the Fermi level be? Closer to the
It's
conduction
for the
band? Closer?
channel, na, sir?
Yes. Okay, I'm also giving you another what to say, like relaxation. Assume the gate is grounded, like no gate voltage. VGS is 0. Okay, where is the Fermi level going to be? Like,
Okay,
in
okay,
which,
okay. Yes, sir.
huh?
In the center, sir?
Center? Why? What is this material over here?
Actually,
It's a P-type
currently,
material.
sir, it's P. Yes, sir,
Yeah.
P.
So the Fermi level is going to be below here.
So P valence band, above the valence band.
Yes, closer to the valence band. Yeah. See, because wherever this Fermi level is in between, it is below the conduction band and above the valence band. So
Hmm.
you have to tell me closer to which it is going to be, so that
Okay.
your answer will be correct in all cases. I want a more precise answer. And finally, we have the drain, where we have same two bands. It's the same as the source, so I'm not asking again. So this is EF, and I have my conduction band and valence band. Okay. Now, when there is contact is established between these three, in equilibrium, what will be constant across them? Like if these three materials are brought together at equilibrium, what will happen?
Diffusion.
No, no, equilibrium. Like no
Okay.
voltages are applied right now. All terminals are grounded, no voltage is applied, there is no charge migration. When equilibrium is achieved, what quantity, what can you say about these three? Like there are three energy levels here: conduction band, valence band, and Fermi level. What will happen to the Fermi level? Will it be the same in all three regions? Will it be different?
The diffusion of charge happen, na? Diffusion of charge carriers.
After all of that, like at equilibrium, equilibrium has been attained. It's a pretty straightforward question. Like, what will happen to the Fermi level when I put these three things together? Like, if I make them get rid of these black lines across the entire device, will the Fermi level be same or will it be different?
Fermi level same, sir.
So that is all. That is all I wanted to know. So at equilibrium, when I bring this together, my EF is going to be the same. So I have EF here, and now because of that, my band diagram will look something like this. Oops. It will look something like, yeah, that was like this. Oh, that's too sharp. Yes. Yeah. And likewise below, rise up. Yeah. So over here again, I can. This thing should be more aligned. Yeah. Uh, no. Again, I apologize for my very poor drawing skills. Yes, something along this line. Oh God. Yeah. So not wasting any more time on this. So yes. So this region is my source, channel, and channel and drain. So this is my conduction band, and this is the valence band. So for this device, for this particular configuration, now tell me what exists in the channel region by default at equilibrium when no voltages are applied. What does the channel region act as? Again, go back to your what to say, like week one content, like in terms of quantum mechanics or things like that. This is how the potential energy profile is varying across the device. So what is the channel acting as? Like, is it a potential well, or is it, what is it, something different?
Potential well like structure.
Is this a potential well, or is it something else? Is what I'm asking. Is this a well?
Potential well, sir.
So the potential is dropping in the channel because this is a well. This is what I will call a potential well,
Okay.
where I have a V naught and the potential falls to some lower level. What is happening here? The opposite of that is happening. So what is that called usually? So this is a barrier. This is a potential barrier over here. Okay.
Yes, sir.
I mean, you can see that, right? This looks like a speed breaker. Like, if electrons are moving from here to here, they have to gain some energy and then lose that energy again. So this is a barrier. So essentially, when we talk about MOSFETs, we are talking about a barrier controlled device. Barrier controlled device. Whereas if you guys remember your basics of electronic devices, you will know that the diodes, not diodes, your BJT's band diagram also looks something like this. But in case of the BJTs, what we shall be doing essentially over there is we'll be trying to influence the carrier injection. Like, I will manipulate the base voltage to make sure more minority carriers are injected into the base so that it can aid the transport of charge carriers from the collector to the emitter. Like, do you guys remember that?
Yes, sir.
So that is a charge control device. But here, what we will do is we will not be injecting any extra charges. What we will do is we will try to raise and lower the height of this barrier. We will try to change the profile of this barrier over here to enhance or reduce the current flowing from the source to the drain.
Yes, sir. With the
You guys
help
should
of
know.
voltage.
Yes, exactly. So this is a barrier controlled device. Now, how is the barrier controlled? It is controlled using uh, so this
That
control
Y
is
direction.
both VDS and VGS. Why?
Yes, sir.
Okay, tell me this. If I increase VDS, what will happen to this band diagram? How will it look? I'm not changing the gate voltage. I'm just increasing VDS. In other words, I'm keeping the source and the gate grounded. I'm just increasing VD. What will happen?
You are, sir, increasing VDS means drain is at positive or negative, sir? Positive.
Huh? Like, typically, what voltage will the drain have? Will it have the negative voltage or positive voltage?
Positive.
Huh. So what will happen here?
Actually, that sir, in drain side, the Fermi level shift down
Okay. Okay.
because sir, in the two terminal device, we studied that the source and drain is there and the channel region is there. When we are applying
Yes.
voltage at drain side, that Fermi level goes down,
Uh-huh.
so
No,
it
like,
enhances the charge transport.
all right. Again, what? So you said the drain gets the positive voltage,
Yeah, and source negative.
source negative. Good. So as I'm okay, so in this case, assume that I'm just connecting a positive voltage here and I'm grounding the other terminal. Let us keep the source grounded. Okay, source is not gaining any voltage. Now tell me, if I increase the drain voltage, what will happen to this barrier height? Will it increase or decrease?
Barrier will sir try to decrease that.
Exactly. The barrier height will decrease. Okay.
Yes, sir.
Hmm. So essentially, what will happen is, as I'm increasing VD, or to be more precise, VDS, as we shall see later, what we will observe is my, like, now I'm just drawing the conduction band from now on. I'm not looking at the valence band because we are primarily concerned with the electronic properties. So this barrier will rise like this and it will fall much faster if I'm increasing the drain voltage. This barrier
Mm.
height will get lowered as VD increases. Okay, so I initially it would have been something like this. Now, as I'm increasing VD, it will go down. So, from here to here. So, first thing we have to understand is VDS is used to lower the barrier height. Now, what will happen if I increase the gate voltage? If I increase the gate voltage, what will happen to these potentials? They will move up,
The
correct?
barrier will move downward fast.
Really? Why? See, the barrier is just the potential, it is not the energy. Remember that. So,
Yes,
increasing the
sir.
voltage will just move the barrier up.
Mm.
So, let me remind you this. Like you said, the barrier will move down faster because you were expecting the current to increase, correct?
Yes, sir.
But how does the current increase in a depletion mode MOSFET?
Right, sir. So
Through
basically,
inversion. Essentially, my valence band is pulled up so high that it comes above the Fermi level. Remember?
mm, yes, sir.
So essentially, what we are doing is we will try to achieve localized inversion. Like from a P type, this material will become N type as Vg increases.
Okay.
Okay. Oh yeah, you're right. Yes. So the barrier will come down. Yes, yes, yes. I'm sorry. You're right. Huh. So this barrier will come down and become flatter and flatter and flatter. Essentially, there will be no distinction between these three regions as I'm increasing Vg. And when it becomes almost identical to both of the source and the drain, we say that inversion is achieved. Yeah, you are correct. Apologies. I made a mistake. Okay. So, VG in general, VGS is used to, like, okay, so I need to be precise here. This is not lower the barrier height. This is This will make, okay, so I should be like speak more correctly here. Mm, So, okay, now first case is increasing VGS. Let us talk about that. So, yes, as you said, as I'm increasing VGS, yeah, many of your questions use these concepts. So, you can use this to solve the assignment problems. I will have this going up and coming down like this. Now, I will have a profile like this essentially. So, this is VGS1 and this is VGS2. What will be the relation between these two voltages? Which will be greater? VGS1 or VGS2? Hello.
Yes, sir. Yes, sir.
So which voltage will be greater?
1 minute, sir. VGS.
You gave the answer already. Like the barrier has come down. This is the conduction band. So
VGS2, sir.
yes, exactly. You're right.
Yes.
VGS2 is greater than VGS1. Okay. So based on this, you can make guesses on what will happen to the channel conductivity and things like that. Remember this. I cannot say anymore because that would imply I will, I'm giving you the answer to the assignment question. So I cannot do that. So this is as much of a hint as I can give you. Second, we are talking about increasing VDS. So now this is the transport property essentially. So now when we are increasing VDS, what happens to the barrier is the following. Essentially, I will originally have a barrier that looks like this. But as and when I'm increasing VDS, the on the drain side, I will have a lowering. Like essentially, the source gate region, like the source channel potential barrier will remain unchanged. But as and when I'm increasing VDS, what will happen is this slope will start increasing. Okay, like essentially this will start moving lower and lower and lower for the same
Sir,
reason
you are
because
indicating. Yeah, actually, some word I am getting like drain induced barrier lowering, like that. DIBL.
yes, but that will happen slightly later. Yes, you're right. You're right. You're
Yes.
perfectly right, but that is not exactly this. DIPL, I will tell
Okay,
you
sir.
what it is in a minute. Okay, so
Actually, you told us, sir, induced. That's why that word come into my mind.
okay, fine, fine, good, good, good.
Yes, sir.
So I'm happy that you're saying such things because I mean ultimately those are the things that you have to understand. So over here, let me draw this using dotted lines so that I can clearly show what is happening. So as and when I'm increasing the drain voltage, what will happen is this part will remain roughly the same, or at least I will expect it to remain the same because I'm only changing the source drain voltage. I'm not changing the gate source voltage. So this part of the barrier should remain roughly the same. But as I'm moving away from this energy will go below to whatever new level of VDS I have achieved. Okay. So as I'm increasing it further, like this will go up again and oh no, I should not make it, I should make it look as uniform as possible. So yeah, and also erase this. Ouch. is it so hard to draw? I really wish I could, have some kind of a top-down camera so that I can draw these things easier on a piece of paper. But yeah, infrastructure limitations prevent me from doing that. So again, it will rise along roughly the same line, but after a certain point, it will fall even faster to an even lower limit. So I have VDS1, VDS2, and VDS3. I have 1, 2, and 3. So which is greater? Like what is the order here? Like which VDS is greater? Hello.
Yes, sir.
Yeah. So which of the VDSs will be greater? VDS is which is greatest? VDS1 or VDS3?
VDS1 is large, sir.
So VDS1 is the highest.
Yes, sir. Actually, because one voltage like that, na VDS equal to minus Q something. One
Uh-huh.
formula is there. That's
No,
why
but
whenever we are applying voltage in the drain side, that Fermi level goes lower.
uh-huh.
So that's why I'm telling like that VDS1 is large compared to VDS3.
Why? Like if the voltage is increased, this level has to go down, correct?
Yes, sir.
So if it is going down, the lowermost must have the highest voltage, right? And that is
Yes,
what you
sir.
said for the gate.
Sir. Okay, okay. Yes, sir.
The
But one formula is there, na, sir. V equal to some minus Q times.
uh-huh. Yes. Yeah, you're correct. It is minus Q times the applied voltage, which is why increasing
Yes, sir. Yes.
voltage takes the energy lower.
Yes, sir.
Okay.
Okay, okay.
So,
Yes. Understand, sir.
so VDS3, again, it is the same as what we did above.
The,
VDS2 greater than VDS1. Okay. Now this is
yes, sir.
essentially what is happening to my barrier. Like when I'm changing VDS and VGS, these are the things that are happening in my device. Now,
Mhm.
so far, remember, we have not done any mathematics. We are just qualitatively analyzing the things. And essentially, what we are able to say is increasing VGS will essentially lower this barrier, so that will make the entry of electrons easier. Okay. And if
Yes,
you
sir.
remember, okay, 1 second. Yeah. So if you remember the mm, yes. So if you remember from your previous, like the parts where we studied the band diagram, you might uh, get an idea that the slope of your energy band diagram, kind of. Okay, I should be very careful here. What is the axis here? What is the like? This is the energy. The y-axis gives the energy profile. What is the x-axis? X-axis. What is the
Transport,
x-axis?
transport.
No, x-axis is just the x-axis along the device. It is the position. I'm moving from here left to right. Like, is that clear? Like the
Yes, sir.
x-axis
Yes.
is just the position. Like this is not an EK diagram or anything. This is an energy as a
Mhm.
function of position.
Understand, sir.
Okay. So Here I am. Let me make this arrow slightly more neater. Uh, yeah. So yeah. So essentially, as this slope keeps increasing, what will happen is my quantity, the average velocity quantity that I previously defined, that will increase
Yes, sir.
because my electrons will essentially
Travel
lose, like this
faster.
is the potential energy. So
Hmm.
more potential energy is lost as it is coming down this hill, which implies the kinetic energy is gained. If the kinetic energy is gained, the average velocity is gained. Okay.
Yes, sir.
Okay, so that is the basic idea for these devices. So when we are talking about MOSFETs, this is the essential notion. These are the what to say, like salient points that we are looking at. Now, what more can we say? So this is the band structure picture. Now let us get some idea about the voltage current relationships that we expect to observe, at least from our classical MOSFETs. Okay, now let us look at VI characteristics. So we are looking at VI characteristics. So first we shall see IDS versus VDS. Again, I'm not giving the exact mathematical relations because week one we are not deriving it. So I'm not mentioning it here yet. So tell me for a given VGS, okay, some constant VGS value, how will IDS versus VDS vary?
VGS values are -2 to 2.
No, no, no. I'm not
Just
saying
an
anything about
example.
VGS. For a given VGS
Okay, okay.
value, VGS is fixed. How would I expect it to vary? As I'm increasing VDS, what will happen to IDS? Will it increase or will it decrease?
Current will increase, sir.
It will increase. Okay. So let me say, let me draw a line like this where it is increasing. Now, will it keep on increasing like this?
It will keep on increasing, but some saturation level will also come, sir.
Exactly. Correct. So, now why did it suddenly become a geometric straight line? I did not want it to be a straight line. I wanted it to be slightly curvy. Please stop assisting me in my drawing. Like I'm talking to the software. Uh, I'm bad enough
No, sir, it's good.
as it is. No, every now and then this thing starts interfering with my doodling. Yes, so it goes up to this point and then I get some kind of a saturation. Correct.
Yes, sir.
So similarly, I let us say at a different VGS, I'm getting a curve like this.
Hmm.
And again, it goes like this. Now tell me, this is for some VGS1 and VGS2. What is the relation between VGS1 and VGS2? Again, simply
That's a
use the no, simply use the logic that we have previously used. What will increasing VGS do? It will lower the barrier. What will happen when the barrier is lower? The current will increase.
current will increase, right,
That is
sir?
all. So wherever the current is higher, VGS is higher there. So VGS1 is greater than VGS2.
VGS2.
Okay. SAS like VGS1 is above. Okay.
Yes, sir.
And using this, now we can also define the regimes of operation. You know what? Let me, for the sake of completion, draw a third one where it again looks similar and saturates. Where it rises roughly linearly and then saturates again. So there will be several such curves, and ultimately there will also be a very small curve over here. We shall come to that in a minute. Uh, that will become important later. Primarily now our focus is going to be in the upper region. So now there is a new graph here. Let me call this some VGS 0. There's some special VGS. This is VGS 3. So here
Okay.
VGS is increasing. So again, we have not looked at any mathematical relations. By just intuitively thinking about the barrier properties, we can guess this much about the current voltage relation. Now, why is there a saturation happening? Can you guess? Like, yes, intuitively you said that there will be some kind of a saturation. Now, why is that happening?
It means like, sir, we are getting the constant flow of electron in the device. That's why
Okay.
indicating the
So why
constant
is
current
that
over
constant
there.
flow is coming? Why is the flow becoming constant? As I'm increasing the voltage, the
Because,
current should keep on increasing.
yes, sir, one pinch of condition reached. Pinch of
Uh-huh.
condition like pinch of voltage.
Uh-huh.
The VGS voltage at which the current starts like in constant mode, sir.
No, that is with respect to VGS. What I'm asking is, as I'm increasing VDS, saturation is occurring. Here, VGS is all kept
Yes, sir.
constant. So why is it saturating with respect to VDS? Again, we are just trying to intuitively understand it. We are not setting up any explicit relationship. Yeah. Why do I, see that the, uh, like what, so remember, so go back to the old expression that I gave. IDS is something like of this kind. It is width into QN,
Hmm. VDS into VGS.
not VDS into VGS. VDS comma VGS. It's a function.
Yes, sir.
Okay.
VDS,
Yeah,
comma.
it's not a
Hmm.
product into the average velocity. Again, this is just for an intuitive understanding. This is not the exact formula for the current that will come later. Here we are just trying to understand what are the parameters that are influencing my device. Okay. I'm not even talking about the microscopic happenings in the device. So, which of these quantities is becoming, so if the current is saturating, then either the available charge has to become a constant or the velocity has to become a constant. Which is becoming constant? As VDS increases. Again, take a guess. I'm not asking for any
Yes.
accurate theoretical, answer with some conceptual explanations.
It's like the constant flow of charge.
Yeah, constant flow of charge, but due to what? Like there are two quantities here that are varying. The channel width is going to stay constant. I mean, the channel is not growing or shrinking. There is the charge and there is the velocity. If the velocity is
So the
saturating
effect of
here,
electric field.
no, no. What I'm asking is which of these two quantities
Hmm.
is saturating? Is Q saturating or is V saturating?
Charge. Okay.
So the answer is both will
Charge.
saturate. Yeah, both will
Yes,
saturate
sir.
actually. Okay. So that is why I am
Okay.
getting current saturation here. Although the charge will saturate faster because there is only so much charge my channel can hold.
Hmm.
Okay. So after that, there is no more charge that can be. present. So no matter how much voltage I will apply, that available charge will only move slightly faster. That is why the rate of increase of the current is slow. After a certain point, even that increase will not happen. Even that will stop. But over here, what was happening is the available charge itself was increasing. After this point, the increase of charge is no longer there. After a further higher VDS, the velocity also will stop increasing. That is a separate effect which we will study later. Okay. So now we shall talk about the regimes of operation. Again, just remember these things to answer the uh, assignment questions. So yeah, I should draw it this close. I just put it up. So yeah. So I have my region 1 over here and my region 2 over here. So what is, I mean, this part should be pretty straightforward. Uh, so I have, so what is this region? What is this region?
First one is, sir, ohmic region.
Yeah, so that is the linear region or the ohmic region. You're correct. And the second is the saturation region.
And one is a saturation region.
Yes, so this is the saturation region. Now, so this is the linear or the ohmic region and the saturation region, and the other region of interest is the region below here, which, so this VGS not that I told is essentially what is called the threshold voltage.
Yes, sir.
Okay. So the threshold voltage is the voltage at which my channel becomes capable of conducting. Below that, my channel is not suitable for conduction of electrons from the source to the drain. So the region below that is referred to as the subthreshold region.
Okay, sir.
Okay, now the subthreshold region, now, like, I mean, how do I put it? Like, in terms of BJT, this will be the linear saturation and the cutoff region. So here we call it the linear, the ohmic, the saturation, ohmic or linear, the saturation and the subthreshold regime. So these are the three regimes of operation. Now, quick question. What is happening to the, how do I put it? Okay, so if I want my uh, MOSFET to act as a switch, which region should I move to and from? If I want switching action, which region am I moving to and from in a MOSFET? Am I moving from ohmic to saturation, or am I moving from saturation to subthreshold, or am I moving from subthreshold to ohmic?
Saturation to subthreshold, sir.
Yes. So essentially, when I'm talking about switching, you're correct. So switching, we are moving from essentially to and from.
Yes, sir.
Subthreshold to saturation. Okay. So like to and from essentially. So I should not just write subthreshold to saturation. Switching, we are concerned with this region. If I want to do amplification and other purposes, I would wish to stay in the ohmic region. Okay. Like standard understanding. Now, what would I consider to be a better switching action? Like, what would I call a better switching performance?
Um, it's like a constant one, constant zero, like that.
No, no, no. Like,
One of situation.
essentially, now we have seen a bunch of quantities here. What I'm asking is, which, uh, like, what kind of a behavior do I want to see for a transistor to act as a better switch? Like, for a small change in the voltage, should I have a large change in the current or a small change in the current? Do you understand?
In current, sir.
Huh?
Means you are telling like a switch in switch case we have to move from on to off, na?
Yes.
When it is on, sir, then high amount of current is flowing. When off,
Yes.
then very less current is flowing.
Yeah. So essentially, my delta IDS, or yeah, just 1 second. Let me stop sharing for just a minute. Okay. Just 1 second. Can you see the board?
Yes.
Okay, good, good, good. Because there was, I mean, for a second there was a power outage, so my this thing stopped working. Yeah, I'm glad things are running again. So essentially, what I want is I want delta IDS to be large for a small VGS. Small, not VGS, small delta VGS. Is this clear?
Yes, sir.
Hmm. I'll write it in a. So ultimately, when I'm looking at the band structure and all these things, I will need to, if I want to, what to say, like use my MOSFET in, integrated circuits. Most of the transistors in an integrated circuit act as switches. So since they are acting as switches, I will need this kind of a behavior. Okay.
Mm.
So essentially, if you are given a bunch of IDS, BGS, so if you want to analyze the switching property of a device, the curve that you're supposed to look at is not the IDS VDS, but the IDS VGS. So that brings us to the next curve that we shall see, that is the IDS VGS relation. So IDS
It's
VGS looks something like, so you tell me now, what will happen if I increase VGS? At least up to a certain limit. VDS is a constant.
okay. VDS constant.
Yes. If I increase VGS, current should increase or decrease?
Increase.
Okay. How will it increase? Like, remember, very small VGS implies I'm below the threshold. Correct?
Mm.
So for low voltages, how will the current increase? Will it increase rapidly or will it increase slowly?
Are you drawing something, sir?
I'm not started drawing yet. Like you can see the screen, right?
Okay. Yes,
I,
sir.
I want you to guess. Since you are the only person present right now, I want you to guess. Like, will it increase rapidly or will it increase slowly? For a small VGS, like VGS is zero over here.
Mm. Slowly, sir.
Slowly, very good. Yes, so that is the sub-threshold region. Now this VGS not I called is a threshold voltage, so there will be a VT. Okay, and after that, what will happen?
Mm.
After that, the rate of increase will not. I mean, it will not shoot up vertically,
Increase,
but it will.
increases, sir.
Yes, it will increase much more rapidly.
Yes, sir.
Okay, so it will increase much faster. Like typically, you will see that there is an exponential relation past the threshold region. Like if your conventional MOSFET formula, you will see that a similar relation exists in our case also. So this is what happens. And so what will happen if I increase VDS? Will IDS increase or decrease?
Means firstly it was constant, na, sir. Then right now you are increasing VDS.
Yes. What will, like if I move not increasing VDS, now if I've increased VDS, like VDS is always a constant, so this is for one VDS. Now how will the current look for a second value of VDS which is greater than this value?
Okay, that threshold will increase VT.
Should the threshold increase?
Means threshold will change.
Like will it change? I'm asking you. Actually, it shouldn't. I mean, the threshold voltage is based on the metal oxide semiconductor domain regime. VDS has no influence on that. Essentially,
Okay.
increasing VDS will only give me a higher current. That is all. So I have VDS
Yes,
1
sir.
and VDS 2.
Hmm.
Again, from our old barrier reasoning only. And this is VDS 1. Increasing VDS will
Yes, sir.
increase IDS. Okay. So this is IDS. So here again, VDS 1 is greater than VDS 2. That's all. Of course, below the
Yes, sir.
threshold, the rate of increase will be less. Above the threshold, the rate of increase will be very high. So now this VT is essentially what I identified as VGS not here. Okay. So below that, increasing VGS even very highly will not create an appreciable change in the current. It will be roughly a constant for values below that. But for anything above that, changing VDS will create, like, essentially what I'm asking is what is, if I shift my VDS from here to here, what is the shift in the current? So here you can see that the shift is very small, but over here you will see that the shift is actually enormously large.
Hmm.
Like
Yes,
I
sir.
will have to draw a horizontal line on the parallel to the IDS axis to see how much it has shifted. So after the threshold, at this point, let us say this is how much the current is increasing by. Whereas below the threshold, the
Hmm.
current was increasing by this much. Okay, so that rate is kind of
Yes, sir.
like expanding rapidly. So that is the picture we are supposed to see here. Now, these are the ideal behavior profiles that we wish to observe. So primarily in this week, if you will notice the assignment questions, now I will go back to the assignment questions to kind of uh, show why we have been talking about these things. I just disabled notifications. Why are you? Yeah. So you see, there are like multiple curves. People have asked for certain relations. There are band diagrams. Uh,
Okay, sir.
yes.
Actually, I'm not able to see questions.
Really? You're not able to see this window?
I'm seeing windows, sir, but not the questions, assignment questions.
What are you seeing then?
Means just it's written like wait, sir. Sharing your entire screen or browser like that.
Ah, okay. So for some strange reason, the sharing stopped. Amazing. Yeah, now can you see it?
Now, yes,
So you can see now there some people have drawn some band diagrams. Some people have drawn, now I'm not answering these questions. I've explained whatever is needed to answer these questions. So go ahead and use what has been explained here. In fact,
mm,
at this point, I have given
yes, sir.
almost all
Lot of
the
information.
concepts, yeah, required for these answers. So I hope both you and people who are listening to the recorded version of this video will be very happy with that. Beyond this, I will have to give you the answers to the assignments, and I cannot do that. Like, I'm forbidden from doing that. So
Yes, sir. Yes, sir.
I shall leave the point at that. Okay. So yeah, moving on to the last concept that we shall discuss today are now the realistic effects. Now, these are all the ideal things that we want to see in our device. But of course, things are not always ideal. Some, realistic uh, effects need to be analyzed. So, the first quantity that is observed in light, that is immediately seen, is the effect of the drain voltage on the barrier. So, ideally speaking, what I said is, as I'm increasing the drain voltage, like our original assumption is VDS has no influence on the source channel barrier. So this is the ideal assumption. Okay, but you tell me this. Let us say I have how do I put it? Let us say I have some kind of a surface. Okay, let it be conducting, insulating, or whatever. There is a surface. Now, at some point in the surface, I'm placing an electrode and I'm applying a voltage. Okay, let me move away from the board for a second. Yeah. So I'm having a electrode on a surface where I've applied a certain voltage. Now, and let us assume that the material is not a conductor. So voltage is not, like spreading effectively throughout. It's an insulator. Let us assume right now that it's a semiconductor or an insulator. So ideally speaking, what will happen is the current will, and let me say there is a second terminal elsewhere. The current will only flow between those two terminals. Elsewhere in the bulk of the material, I will not see the effect of that voltage. Correct? That is a reasonable expectation. Is it not?
Hmm. Yes, sir.
But as we are moving closer and closer and closer to the electrode, will we feel the effect of that voltage? I mean, we
Yes,
should,
sir.
right?
Yes,
That's
sir.
kind of what is
Hmm.
expected. So that is essentially what is happening here. So this statement that I just mentioned, that the drain voltage
Has
does
no
not
effect,
have,
right?
yeah, that is an ideal assumption. But in reality, what will happen? So this is an ideal assumption, but in reality, VDS has an effect on the barrier.
Yes, sir, because the channel length is also in the nano level.
Exactly. Has an effect,
Yes.
especially in short channels. So again, yes, the effect that we are going to analyze is a very complicated effect. There will be formulae, there will be equations. But even before you go to the equations and the formulae, you should understand the reason why this is happening is very straightforward. The electrodes and the material, they're all very close by. They're only a few nanometers apart. So as much as
Yes,
I
sir.
would like to have the two things to be isolated, they can no longer be isolated. If they have to be isolated, then I need to have long channel devices. If I have long channel devices, then my transistor count on the device will reduce. If the transistor count reduces, then the potential computational power comes down. But we want more and more powerful processors for our smartphones or smartwatches or whatever. So, we need short channel devices. At least that is our demand. Moore's law says that, it will keep doubling every few years and so on and so forth. So, especially in short channel devices, has an effect on the source channel barrier. So, this is what is known as drain induced barrier. Here, let me make the induced capital lower, or this is what is called DIBL. So what happens is, as and when I am increasing VDS, so this is what I expect to happen. But what will, like, ideally speaking, I will expect this to stay fixed, this point to stay kind of fixed, irrespective of my drain voltage. But in reality, what will happen is this will also get lowered. So this barrier will also like keep getting pulled below and below and below.
Nice.
Okay. So this
Yes, sir.
drop is essentially what is happening in the case of DIBL. This is drain induced barrier lowering. And this effect will become more and more profound the shorter my channel gets. Okay. So now, how do we, of course, like I'm not going into further details again, because if I do that, I will be answering one more assignment question. I'm not going to do that. I hope that you guys will listen to the lectures to understand that part. So now, of course, this is happening, but we need short channels. So how do we prevent this? Like we have to find some way of preventing it, right?
Mm.
So how do we do that? So those are the things we shall be looking at in the next week. Like right now, I am not going to give an answer to that. So essentially, so right now, this is like my, yes, my source channel drain, CN drain. And so over here, this barrier gets lowered because of my applied VDS. So I have my VDS on this end, I have my VDS on this end. So VDS1, VDS2, and typically VDS2 here is greater than VDS1. So just like I expected the drain voltage to fall because of increasing VDS, but what happens is it also lowers the barrier. So qualitatively, can you tell me what will this do to the current? Will it increase the current or will it decrease the current?
Sir, current will increase.
Why?
Actually,
Remember that the height of this barrier, higher the barrier, the greater the velocity of the electron entering the drain. Lower the barrier, lower the velocity.
Okay.
So that is what happens because of DIPL. What
Understand.
it will do is it will actually, yes, more charges will come, but they will start coming in slower. So it will kind of drag my current down. Of course, more charges are available, but because this barrier height is low, my drain is no longer able to drain the electrons efficiently. It is actually lowering like it is reducing the charge accumulation capacity of my channel.
Okay,
And
sir.
it is
Okay.
affecting the transport properties. So because of that, what will happen is my current will kind of slide lower in spite of the fact that this barrier is falling.
Yes, sir. Means the drain is not effectively collecting that
Yes,
charges
exactly. So that is
because
what
of
will
this.
happen. So now, because of that, you will see that certain current properties will change, and I mean that will
And
be explained in the lecture. I'm not going like I will not repeat the content. So that is
uh,
essentially what is like, and that is an undesirable property. Of course, you do not want that, especially if you want a switch, because over here this is kind of impeding the effect of my VGS.
hmm. Yes, sir.
So I do not want that, especially if I want to build a good switch. So DIPL is very dangerous for switching devices, and most of our transistor fabrication is primarily for building switches. So this is a very
Hmm.
bad property in that regard. Not bad; it is an undesirable property. How to eliminate this in a short channel? We will see more about that in the next week. So with that, I think I will stop today's session.
Yes, sir.
Uh,
Clear.
Okay, so with this, we shall stop at today's session. We've had what? Yeah, nice. So that brings us to the end of our discussion for this week. Next week onwards, we shall resume at the standard time. So we shall meet on Saturdays 3 to 5. Yesterday and day before, I was traveling, so I was unable to take the session
No issue,
the
sir.
allotted
Today
time.
is Sunday became great because of your lecture. Thank you.
Oh, well, I'm glad that is the case. Yeah. Um, yes, so going forward, we shall essentially look at the various effects that are occurring due to like the electrostatics and the transport properties, and try to quantify them and see how the device geometry and the device construction can be used to remedy this. So the solution to the problem that I mentioned is we need to tweak the geometry of our device slightly in some
And
way. Huh.
and sir, one just maybe it's like suggestion or question.
Uh-huh.
So can you show some like example like maybe some IEEE paper to show some transport property how
Sure.
somewhat like that?
And maybe not the next week, but the week after that, I will share some papers. Yeah, that will actually
No
be
issue,
helpful.
sir.
Thank you for the suggestion. I
Yes,
will get some papers that I can access and show over our call, because some of them are restricted access. But open access papers that are present, I will share some of them, and I will show how these properties are analyzed, because as you are moving to the more advanced topics, you will find that it is hard to get some textbook material also. Like even
yes,
when
sir.
preparing the questions for your course, I faced that challenge. So I had to read some papers and get some ideas, borrow some ideas from them, and make some elementary questions based on the things that I studied there. So
Because
especially when
sir,
we are talking, huh?
yes, sir. Because why I'm telling that because
Hmm.
already we are understanding how things are getting from like transport from source to drain, but
Hmm.
in the real life scenario, the graph showing like how this affects
Hmm. Hmm.
because
Hmm.
they are dealing in a very vast
Yes,
application,
yes,
na?
yes.
So that's
So a week after next will be the ideal time, because at that time you shall talk about silicon on insulator devices. You shall talk about single gate versus multi gate devices, and other such things will show up. So in that case,
yes,
I will pick up some papers where these devices are analyzed, and I shall show you the current voltage characteristics, at least according to their simulations and
sure, sir.
tests, so that you can see these effects in action. Yeah, I will
Yes, sir.
definitely do that.
Yeah. Thank you
Yeah,
so
all
much.
right.
Yeah.
So once again, thank you to Kamal for staying till the end. A bunch of other people came in and moved. I suppose they were busy with some other activities. It doesn't matter. So yeah, thank you once again for listening. Next week
Thank
onwards,
you
we
so much.
shall resume our sessions on Saturday from 3 p.m. to 5 p.m. So that is
Yes.
all.
Okay, sir.
I shall end the call now. Yeah, thank you.
Yes.